Thank you. Thanks. Morning, everybody. So we talk about change in the software industry a lot, and I think that's fair. There's a lot of change that goes on. But I think that there are different kinds of change, and there's a significant amount of the change that goes on in our industry that's kind of a little bit ephemeral. It kind of happens, but it doesn't matter that much. If I'm honest, I don't really mind too much about the latest JavaScript libraries this week. There'll be some good ones and there's some bad ones, but it's not foundational. Periodically, though, I think that what we see is that we see a different kind of change come along. I think we see a change come along that represents a step change in our ability, the way in which we think about software development, the way in which we approach it. And I believe that continuous delivery is one of those kinds of things. And you may say, he would say that, wouldn't he, because he wrote a book about it. But I think it's deeper than that. I think that what we've found is that I think we've found a way of approaching software development that's much closer to a genuine engineering discipline. And as you would expect, if that were the case, we see that it's more efficient. It allows us to produce higher quality more quickly, more effectively, pleasing our users. And ultimately, it makes the organizations that practice it more money. I'm going to try and convince you that some of those statements, if not all of those statements, are correct over the next 50 minutes or so, and try and describe what it is that we're talking about and why I think it's important. I think a good place to start is to think about what is the performance of the software industry? How does that go about? And I think it's sensible to be wary of these kinds of surveys of software projects. They are not scientifically controlled experiments. We're going to talk later on a little bit about some things that are, but these are not. This is not data that you can kind of absolutely trust, but nevertheless, they give us some kind of subjective impression, and they tend to tell a fairly consistent story. And if we're honest, that story is a little bit depressing if you're a professional software developer, as I am. This last one, if you're interested, if you're a fan of Schadenfreude, this last one's amusing in a warped kind of way. In a study of nearly 6,000 projects, 17% of them go so badly that they threaten the existence of the company that began the projects. That's not really a story of success. I think that if software projects were normal things, there ought to be a normal distribution of software project success. As many software projects ought to be finishing ahead of schedule, under budget, delighting their users, as finish behind schedule, over budget, and pissing off their users. And I don't think that's what we recognize as normal for our industry, if I'm honest. I think that the curve that we think of as normal for our industry is much more like that. And that says several things. One, it means that we approach projects with a degree of trepidation and a degree of fear. It means that we're going to be much more careful about the way in which we think about starting them off and all that kind of thing. But I think it says something more profound than that. I think I'm just going to say what I said again. If software projects were normal things, there'd be a normal distribution. The fact that there's not a normal distribution means it's not a normal thing, which kind of means we've got the model wrong. It means that there's something fundamental in the way that we think about and practice software development that's wrong, I would argue. I love this little GIF animation. This is kind of my stereotype for paradigm shift. This is a little animation of the orbits of the planets based on two different models of the solar system, the geocentric and the heliocentric view of the solar system. On the right-hand side, the geocentric view of the solar system was the one that was held by humanity for tens of thousands of years. We kind of assumed that the Earth was at the center of the universe, that all of the things in the sky went around the Earth. And that makes sense when you look at the orbit of the sun and the stars, and then you look at the planets and you go, well, those are screwy, what's going on there? The term planet, it comes from ancient Greek, and it meant wanderer, and it's because they were wandering about all over the sky, and it didn't make any sense. Some of the cleverest machines that had been built at this point in history were built to try and predict these orbits, these epicycles, as they were described, this complexity. The trouble is if you live in that solar system, Newton can't come up with an inverse square law. He doesn't predict those orbits. It doesn't make sense. Einstein can't come along a little bit later with bendy sheets of space-time and general relativity. Those ideas are not conceivable in that solar system. The only way that you get to think those ideas is by stepping out of that solar system and standing in a different one, which is what Copernicus and Galileo did a little bit later. They said, no, that's the wrong model. It's the sun that's at the center of the universe. That was wrong, but it was a better approximation. And in our gravity well, inside of our solar system, it gives this prediction of the orbits that are essentially elliptical rather than circular, but it gives a much simpler model. Even I couldn't do the maths to figure out the orbits of the planets in that kind of solar system. Newton can come along and come up with an inverse square law. Einstein can come up with bendy sheets of space-time. We can start to have new thoughts. I think this is a pretty accurate analogy from my perspective about what software development industry looks like. I think that much of software development is living in a geocentric solar system, and we add complexity on top of complexity in order to try and cope with what we think of as a really intractable problem of software development. And I think that's a mistake. So I would argue that the state of software development has been somewhat less than optimal. And I would argue that in recent years we've started to find some answers. It's not smooth and polished. It's not cookie cutter. This was clearly built in somebody's shed, but it is a motorbike with a jet engine attached. And I think that's a reasonable kind of, again, a reasonable analogy for what we're talking about. So what have we looked at over the years? We've looked at other industries, and we've tried to learn the lessons from other industries and apply those to our development. We've come up with waterfall models. We've come up with V models. We tried to divide the problems up into smaller pieces. And Michael, in his wonderful keynote, was talking about the problems of coupling and the couplings that we get organizationally as well as technically kind of follow from these kinds of things at some level. We tried thinking more iteratively and trying to think about better ways of working. We've tried project management approaches like Scrum to move forward. We've tried extreme programming, bringing some engineering into the approach. We've tried hiring really smart people and putting them in a corner somewhere. We've tried hiring young smart people because they're cheaper. And we tried hiring young, smart people in foreign countries because they're cheaper too. And none of this has really answered the question. None of this has been a slam dunk. None of this has kind of solved the problem. It kind of paints a picture of our industry. Interestingly, this is one of those points where you can kind of point to a particular document, a particular moment in history and say, oh, why did we do that? This is the paper that introduced to software development the term waterfall for the first time. So this was a publication as part of an IEEE conference published in 1970 by Dr. Winston Royce, advertising the ideas of approaches to software development process. This paper is about 15 to 20 pages long. This famous diagram that we've all seen is on page 2. So you can imagine, you're a busy person in the 1970s with your flares, and you're going to look at the paper, and you're going to say, oh, I get that. I'm not going to read the whole document. It's too long. But it's on page 2. It's obvious. We'll do that. It's easy to remember. I can go and write it down on the 1970s version of a whiteboard, which is kind of a shame, because if you'd read the next paragraph, let alone the rest of the paper, it would have said something else. I've blown it up so you can read it. It says, the implementation described above is risky and invites failure. It says the testing phase, which occurs at the end of the development cycle, is the first event for which timing, storage, input-output transfers, etc. are experienced as opposed to analysed. These phenomena are not precisely analysable. So the paper that introduced waterfall to our industry said, whatever you do, don't do waterfall. That would be stupid. And Mr. Royce spent a lot of the rest of his career saying, no, I didn't mean that. But this is the diagram that he was recommending. I have to agree with you, it's not quite so instantly memorable. But with the perspective of 21st century hindsight, it's fascinating. If you read this, it says, involve the customer. It says, you must do it twice if you can. It says, you must involve feedback from testing into development and from development into requirements. I think if we thought of that with the perspective of a 21st century perspective, we'd probably call it an agile method, is what it was really describing. So the paper that introduced waterfall was saying, let's do something iterative, let's do something experimental. Interesting. This is a picture that was taken in the west of Ireland, in the British Isles where I come from, and you can see that there's been an unfortunate accident and there's a car has driven off the quayside. So what do you do under these circumstances? You go and rent a crane. Oh no. What do you do now? Bigger crane, thank you for playing. Yes, you get a bigger crane. Can you see where this is going? Einstein said that insanity was doing the same thing over and over again and expecting different results. So if our software development processes don't do exactly what we want them to do, we should try something else. We should try anything else, really. If they're not working, do something else. Don't do the same thing, but harder. I think if we start thinking about that, a good place to start is here. I would make the suggestion that any organization that's creating software for any purpose wants this. They want to be able to have an idea, they want to be able to get that idea out into the hands of their users, and they want to figure out what the users make of the ideas. I think that pretty much is it. I think if we think about it kind of from a reductionist point of view, all of us in this room at some level are employed to achieve that. So that seems like a good place to start if we want to think about what a software development process should really look like, should really work. We should work to optimize that. I want to pose you a question. So what's the most successful invention in human history? And here are some pictures intended to mislead you. Anybody suggestions? Sorry? The wheel. I have some words. Writing. I think writing's quite a nice one. Alphabets are interesting because alphabets, not just writing, but alphabets are kind of, they're infinite. You can write words that you've never seen written down before. They're quite clever things. Language, maybe, and all that sort of thing. I think those sorts of abstract things are in with a shout. And I would argue that this is the most important thing, the invention in human history. If you look at human progress on almost any scale, we've existed as a distinct species for around about, there's debates, they're pushing the date back at the moment, but it's over 200,000 years. So let's say 250,000 years. 250,000 years ago, the people on the planet were identical to us. They were just as smart as us. They had the same number of neurons as us in their heads. They were us. But human history, on almost any scale, is a flat, any scale of progress is a flat line for 200,000 years, and then more than 200,000 years, and then it ticks up about 300 or 400 years ago, and then it goes exponentially any non-logarithmic scale. It's a straight line across the bottom, and it's a vertical line straight up. If you look at the resources that we consume, the distances that we travel, the information that we process, all of these things, there's data that says that the whole of human knowledge is doubling every 14 months. That's staggering thought. 200,000 years worth of information every 14 months is where we're at the moment. What happened about 300 or 400 years ago that started that? Well, it was the age of the Enlightenment. It was the introduction of the scientific method. It was the starting to think in scientific, rational terms and applying that kind of thinking to solving practical problems. We call that engineering, the practical problems bit. But that was the difference. That was the thing that stopped us from an essentially agrarian economy and tipped us into the beginnings of an industrial economy and later an information age that we're in the middle of now. That was the difference. And by science, I don't mean space shuttles and large hadron colliders and modern medicine. I mean this. the simple four-step method of solving problems. The thing that Richard Fineman calls is the tool that stops us fooling ourselves. We are very prone to jump to conclusions and make the wrong decisions, and so we protect ourselves from that propensity by being skeptical, by testing things and capturing data, getting evidence for the things that we believe in. So this is what Wikipedia says the scientific method is. We make a guess based on experience and observation. We propose an explanation for what it is that we observe. We make a prediction based on that explanation, and then we test the prediction. And then we observe what happens from that, and we decide what to do next. And that's the thing that's enables us to do clever things. It's the thing that allows us to build machines like this, and the computers that we work on, and the aeroplanes that we fly on, and the materials that we wear, and all of this stuff is the functioning of that kind of thinking. And I would argue that for most of us, and certainly for most of my career, bears very little relationship to the way in which we approach software development. Most of the software development that I've worked on through much of my career was really based on guesswork. We'd guess about what it is that our users wanted. We'd guess about whether our solution might fit that need. We'd guess about whether it's going to be maintainable in the future. We'd guess about whether it was going to be fast enough, resilient enough, scalable enough. We'd guess about whether it had any bugs, and we'd put it out into production, and usually it did. And we'd be making lots of these guesses. And I think that there are ways of working that allow us to get a little bit beyond that, and so instead of guessing, start experimenting and start measuring. And I think that's one of the fundamental things that we're talking about here. I like this little model of continuous delivery. It's an abstraction, it's a simplification, but it's trying to point out the dramatic importance of feedback. We've got these multiple layers of feedback. And there are many, many, many more layers of feedback than this involved in a software project. But these seem to be core to a continuous delivery process. So at the outside, we're going to have this big feedback loop, our raison d'etre. We're going to have an idea, get the idea out into the hands of our users and figure out what they make of it. At the inside, we've got the really tight, fast feedback loop of test-driven development. We're going to build a test and run it and see it fail. Write some code to make it pass, run it and see it pass, refactor and tidy it up, commit, move on. And in between, we've got testing from other perspectives, from the perspective of the user of the system, and performance testing and all those sorts of things. And these things give us learning opportunities by establishing these things as closed feedback loops. You might be able to tell from the tone of my conversation that I'm a little bit of a popular science nerd, and this is one of my heroes. This is Richard Fineman, a Nobel Prize-winning physicist. If you haven't come across Fineman, look him up. You will thank me for that, because he's a fantastic, fascinating individual. He's probably one of the smartest people that our species has created in terms of his impact on things. But he's also a bit of a philosopher on the subject of science, which is what I'm using for in this context. It doesn't matter how intelligent you are, and this is a first-class Nobel Prize-winning genius saying this. It doesn't matter how intelligent you are, if you guess, and that guess can't be backed up by experimental evidence, it's just a guess. So let's start moving away from guessing, and let's start moving into the territory of testing, evaluating, experimenting. I think if we stopped now and you went away and you applied that kind of stuff to your work, I think you would see an impact. But there's more. You'll be pleased to hear, because I'm not done yet. This is one of the things. We've got a measuring stick. This is the idea of cycle time, and this is a proxy measure for the thing that I said about having an idea and getting software out into the hands of our users. This is a way of evaluating your software development process and understanding where the costs and the inefficiencies are. The thought experiment is this. So imagine a single line change to your production system. Any change, doesn't matter, but it's a simple change. So the actual piece of work itself is negligible. Now imagine that change going through your normal development process, going through all of the stages as it should. So somebody's going to agree that the change should be done. Somebody's going to figure out which team it should be done in. Somebody's going to turn that into a requirement that feeds in the team in some way. The team's going to pick that requirement up. They're going to develop it. They're going to test it. They're going to deploy it. They're going to monitor it. All of those things, all of those bits and pieces, and you kind of just measure the time, how long each of those activities takes you. I'm going to show you 2 cycle times from real projects that I worked on. The first one was an order management system in a bank. I can even tell you which bank it is because it's long ago now that I don't have to protect the guilty, because this was years and years ago. This was Barclays Bank. It was an order management system that I worked on as a consultant. And the cycle time for that organization, for this project, was 103 days. If you've got a single line change, if they followed their own processes, they couldn't get into production in under 103 days. If it takes you 103 days to get a single line change into production, you don't have a feedback loop. Somebody comes to me after 103 days and says, Dave, you've just broken production. I'm going to say, what? I say, couldn't possibly be me. I was on holiday. And I'm going to say it wasn't my change. It was my change and your change, and they bumped into each other and they caused a problem. And I might be right, because what's happening is if you're only going into production once every 103 days, what you're doing is that you're dumping a huge pile of changes into production, and the chances are that one or more of those changes might interact in unpleasant ways. They might trip each other up, and they might cause a complicated problem. We're going to have to think really hard to figure out what's going on. So it's quite a risky strategy. This is another cycle time. This is a cycle time. I had the privilege to be involved in one of those projects that you can kind of look back and smile on. It was a startup. We were doing some seriously, interestingly tricky technical things. We built one of the world's highest performance financial exchanges from scratch, from a blank sheet of paper. It's a lovely kind of opportunity to do that sort of thing. And it was in the middle of while I was writing the continuous delivery book, and my job was head of software development. So I had free rein to try and brainwash everybody to approach this in a way that I thought would work. So we did it as a continuous delivery project from a blank sheet of paper. In terms of scale, the project on the bottom was probably, just rough numbers, somewhere between 15 and 20 times bigger than the project on the top. And we could make any change to any aspect of our production system, evaluate it so there was no more work to do, and get an answer, a definitive answer was, are we safe to go into production or not? I'm going to revise that. Are we comfortable with going into production or not? And we get an answer back in 57 minutes. That's game-changing. That entirely changes your relationship with your software and your software development process. If you can try anything out in 57 minutes, you will. So we used to, our software was built in Java. We used to take the latest version of Java the day after it was released, and we would just put it through. If it passed all the tests, it would go into production the next time it was released. That alone closes a whole load of security areas. If you do that with your operating systems as well, you don't really have, you massively reduce the attack surface area for security. We decided that we didn't like the relational, commercial deal that we had with our relational database vendor for our data warehouse. So we swapped it out for another one. It took half a morning to write the automated script to deploy the new open source version of a relational database instead of the commercial one. We put it through the pipeline, and we got a couple of test failures. We corrected the problem, we put it through the pipeline again, all the tests passed. The next time we deployed into production, it went with a new database version. I've worked places where just that would have probably been a project for 6 months or a year. So this fantastically, dramatically changes your relationship with your software and your development process. I think the combination of these two ideas is quite profound. So first, if we work in this experimental, iterative, empirical discovery kind of approach, we capture evidence about the choices and the ideas that we have, and we make decisions based on that evidence. And we use that power, that superpower, to optimize our development process to reduce the cycle time, we drive out pretty much all of the agile theory, all of lean theory, all of DevOps theory, and all of continuous delivery theory as a side effect. You can't have a 57-minute cycle time if your team is too big. The communication overhead will kill you. You can't have a 57-minute cycle time if your organization is siloed, because the handovers will kill you. You can't have a 57-minute cycle time if you haven't got a great argument in terms of configuration management, build automation, test automation, deployment automation, all of that stuff, monitoring in production, team collaboration. You've got to be good at all of those things. And that's one of the gotchas. Remember my picture of the paradigm shift? One of the things about shifting the paradigm, continuous delivery is going to bring enormous value. It's enormous. We are often talking, we're not talking about 5 or 10% increments in the quality of the work or output or efficiency here. We are often talking massive steps forward, sometimes orders of magnitude in certain measures. Steps forward. The trouble is, in order to do that, it's a big shift in the way in which we think about and approach software development, and you've got to be good at lots of stuff to make it work, which is the downside. So what is it that we're talking about? The phrase continuous delivery comes from the Agile Manifesto, the first principle of which is our highest priority is to satisfy the customer through the early and continuous delivery of valuable software. Have an idea, get it out into the hands of users, and figure out what they make of it. It's the logical extension of continuous integration. Continuous integration is the practice that was kind of popularized at the start of this century, really. There were a few people that were employing it before that, but that's when it became widely used and widely known. And that gave great feedback to development teams about fail fast on their changes, their technical changes. And continuous delivery is really kind of extending the range of that thinking just to a little bit further out into the development process. A little bit more upstream, a little bit more downstream. I think of it as this holistic approach to software development. You can't really do, it's not just about test automation or deployment automation or build automation. That's not enough. If you only do those things, it won't work. You might get some advantage, but it won't be the kind of transformative change that we're talking about. It's this holistic approach. It touches on nearly every aspect of software development. It leaks out. It starts to change the way that organizations work. If you look at the organizations that are world class at this kind of thing, they don't look like traditional organizations. They work in different ways. A great mental model for this thing, I think, is that if you imagine that every single time that you commit any change that's destined for production, what you are doing is that you're giving birth to a release candidate. And the job of your process and your technology from now on is to prove that that release candidate is not fit to make it into production. That might sound backwards at first, but this is another lesson that we learn from science. We can never prove that our software is good. That's why I stumbled over my statement earlier on. We can never prove, we can never assert that our software is good. But as soon as we can identify that it's not good enough, as soon as we have one test that fails, we know that it's not good enough, and therefore we can reject the release candidate. So we can use falsifiability in our development process to drive us forwards. Use testing as a falsification mechanism. That starts to say something about the seriousness with which we're going to treat our tests. We need them to be reliable. We need them to be efficient. We need them to, when they fail, we're going to believe them. We are not going to run them again and cross our fingers and hope that the time when it passes is the time that's true, rather than the time when it fails is the time that it's true. Finally, often in Scrum, people will talk about definitions of done. I think the definition of done is not quite this even. So finished means released into production. Not quite. Finished means in the hands of users delivering value. That's really when we're done with any particular change. And so we need to think seriously about how we close that feedback loop. How do we get telemetry back out of production and into our development process so that we're able to learn? We're trying to create a repeatable, reliable process for releasing software. We want to automate if we want it to be repeatable and reliable, kind of rules us out as a species. We are not repeatable and reliable. We're rubbish at being repeatable and reliable. We're brilliant at other things, but repeatable and reliable ain't it. So if we want to be repeatable and reliable, we're going to automate I've put almost everything, and I'm getting harder line as I get older. We're going to automate everything, pretty much. I'm not sure what we're not going to automate. The only things we're not going to automate are kind of really sophisticated, clever human decision making. Everything else we'll automate. If we want to automate everything, we're going to version control everything. Not just our source code, but its configuration. I want another little thought experiment. Imagine being able to release a version of your production system that was running in production 2 years ago into a test environment at the push of a button. If you could do that, it's saying that you've got a pretty thorough picture of the configuration management and all of the dependencies that are relied upon. That release candidate is going to know what version of the operating system it needed, what version of the relational database management system it needed, what schema it was running against. Everything, all version controlled. We want to bring the pain forward. If something's difficult and painful, we're going to do it more frequently. We're going to up the volume so that we're going to surface the pain. We're going to surface the problems so that we can identify it and we can address it, largely automate it away or refine our processes to encompass that, and then we can solve the problems and move forward more effectively. We need to treat quality as a first-class, vital aspect of everything that we do. We need to be much more focused on quality. I had an interesting conversation with a developer last year who I was trying to encourage this team to practice test-driven development, and they weren't. And this developer, I said to this developer, why don't you do test? You know you're supposed to write the test first. Why aren't you writing the test first? And he says, well, we don't always get our estimates right. I said, well, no, who gets their estimates right? So what we do is that we write the code first, and then if we run out of time, we don't have to do the testing. That's a terrible idea. If you write one test, and you run that test from now on, you've solved a problem. That's a problem that you're never going to have again, because the test is there. It's the defense against that problem. And so if you keep running it, you're never going to get that problem again, which means that you're not going to pay back sometime in the future because of that problem. If you do lots of testing, you're going to reduce a lot of problems. So you get this massive payback. All of the data from the industry says that if you do a more thorough job of automated testing, you dramatically improve your position. You're going to do work in odd places. You're going to spend a lot of time working on automated testing and so on, but you build it into your development process, and you save time on going and fixing problems in production. The system that I based my description on earlier on, the exchange that we built, we were in production for 13 months and 5 days before the first bug was identified by a user. That's quite surprising. I've not worked on a system like that before. And that's a huge saving of effort in terms of development teams. I'll show you some numbers later on in terms of the efficiency impact that kind of thing has. And finally, finished means in the hands of users delivering value. Oh, sorry, I must have skipped back. I was talking about the wrong slide. Where were we? Building quality in. Done means in the hands of users delivering value. Everybody's responsible for the release process. We want our processes to be transparent and obvious to see what's going on so that everybody can be involved. And this is not a kind of process where you can buy a book, even my book. You can't just buy that and you're now done to continuous delivery. You're not going to buy a tool off the shelf and you're doing continuous delivery. This is a change in the way in which you think about software development. And once you've drunk the Kool-Aid, I'm sorry to tell you, there's a part of you that's going to be permanently disappointed, because however great everything is, our build is 4 minutes long. Oh no, can we make it 30 seconds? That's the game that you're in forever from now on. It's just improving, always looking better. This is me showing off. If agile development was the opening act to a great performance, continuous delivery is the headliner. I think that continuous delivery is quite widely seen these days as pretty much state of the art in software development approach. I think this is the best that we know how to do at the moment. If I'm honest, this may sound hubristic, for which I apologize because I'm English, but if I'm honest, I think that Software development in the future will look more like continuous delivery than it looks like anything else. That will probably be called something else. There might be different aspects to it, but it's going to be iterative. It's going to be automated. It's going to be based on feedback. It's going to be, it's going to be this kind of deterministic engineering process because it works better. One of the core ideas is this. This is the idea of the deployment pipeline. And the idea here is that we're going to push all changes destined for production through this same mechanism. We're going to evaluate those changes on a number of different fronts. Developer's going to commit a change. It's going to go into the version control system, and that's going to. Sorry, I said a developer. Anybody is going to commit a change that's going to go into production. Operations person, developer, QA person, anybody, whoever it is. Anybody on the team going to commit a change. It's going to go into the version control system. That's going to trigger an evaluation, and we're going to run some tests. We're going to run a lot of tests. What we're looking for at this early stage of the process is that we're looking for two things. Fast feedback, ideally feedback in under 5 minutes, and a high level of confidence that if everything passes in the commit stage, everything else is going to be good. And then the developers or whoever else are going to move on and start thinking about and working on something else. Meantime, the less efficient, slower kinds of evaluations, still under an hour, that need to go on, things like user-centered testing from the point of view of a user, deploying the system into production-like test environments, evaluating it from the perspective of an external user of the system in lifelike scenarios, testing the deployment of the software, the configuration of the software, everything else, that's going to start as well. And then there might be, and we're going to do all regression testing on an automated basis in this approach. We'll use human beings for the things that human beings are good at, sort of exploratory testing, and does it paint pretty pictures inside my head? Is it nice to use? Does it allow me to extrapolate and understand where I'm going to go next when I'm using it, that kind of thing. We're going to do performance testing. We're going to evaluate the software. Is it fast enough? Is it resilient enough? Is it scalable enough? Is it secure? We're going to test everything that we can think of, in essence, on an automated basis, and we're going to get an answer back in under an hour. That's what we're trying to do. We're trying to get an answer to a point where we're comfortable to be able to release change into production multiple times per day. If all of this stuff works, we're kind of comfortable to go into production. We could either, just depending on the nature of our business, just say, this is good, let's just push it into production. Or that's called continuous deployment. Or we could, maybe that doesn't work for our business. We could say that release candidate is qualified to go into production, but we'll decide when we release it as a separate step. Both of those strategies work. It's not necessarily to automatically push into production. One of my preferred definitions of continuous delivery is that continuous delivery is working in a way so our software is always in a releasable state. Sorry, let me just step back. And just make you think for a moment. Just think for a moment about building a machine like that, and think about trying to build a machine like that where you don't have complete end-to-end traceability of everything that's going on. If you work in a regulated environment, I would argue that this is pretty much the only way in which you get the kind of insight and traceability that modern regulatory frameworks are looking for. And you get it as a side effect. You get it as a default. You have all of the information, the whole picture of all of the meta information about what went into creating and managing and evaluating a change as essentially a searchable space that you can kind of pull out information from and paint pictures from and build reports against. So at this point, I sometimes get some pushbacks, and at this point, I've usually bludgeoned people into a sense of resignation, and they will say something like, "Oh, okay, it sounds like it could work, but it's only for small projects, right?" And my answer for that is Google. So Google currently have 9.5 billion lines of code, I read somewhere recently, and a large proportion of that 9.5 billion lines of code is in a single repository. Pretty much everything except, I think so Android and I think Chrome are not in that big repo, but everything else is. And they've had continuous build and continuous test on that massive repository for years now. This data is quite old now. This is quite out of date. I don't know what the numbers are at the moment. But about 3 or 4 years ago, they were talking about doing 100 million test cases a day. It scales enormously. If you have more than 100 million test cases a day, I'd be really interested in talking to you. But otherwise, shut up. You can do it. The other pushback that I get is sometimes people confusing continuous delivery with continuous deployment. The continuous deployment is the automatic push into production, which is okay, because continuous deployment is really good. But they'll say things like, our release process is horrid. We release once every 6 months, and it's a nightmare. I have sleepless nights before I come up to releases, and you want to release how often? Are you insane? And my answer for that is the Amazon build process. How many people have used Amazon in the last 2 weeks? Which version did you use? That's a stupid question, which not even Amazon could answer, because on average, Amazon are pushing a change into production once every 11.6 seconds. On average, that change is going to 10,000 servers. Since they've been doing that, they've seen a massive reduction in outages caused by change and the cost of recovering from those outages. Less than 1,000% of deployments cause a change, which is still quite frequent if you're doing once every 11.6 seconds. But they're so tiny, each change is so small and simple and easy to reason about, it's trivial to revert it if you need to. The next pushback that I sometimes get is, okay, all right, so it works for simple problems like Amazon and Google, but my software is hard. I don't know why, but my client base involves quite a significant amount of hardware as well as software these days. This works well in those circumstances. The canonical example, though, is the HP LaserJet firmware team experience. The HP LaserJet firmware team, back in the mid-2000s, there were about 450 people, I think spread across 2 or 3 sites around the planet. And they were in a mess. They were in a very unpleasant place. They had a requirements backlog of stories that was 5 years long, was their estimate. The rest of the organization had literally stopped asking for any new changes because they knew that they were never going to get them. They got quality problems, all sorts of things. Interestingly, they did an analysis of where their development efforts were being spent, which is captured here. In 2008, 5% of their global development effort was being spent on what they call here innovation, what you and I would just call new features. This isn't hard science research. This is just building new features when they say innovation. 5 times as much effort was spent on porting code between branches. 5 times as much effort was spent on support by the development team of the software. And so they stopped and they kind of said, this really isn't working very well. Let's think again. And so they kind of went through the process that we've been through. So let's get, what do we really want? Well, we'd like to have an idea and get it in the hands of users. Let's optimize for that, and so on and so on. And they evolved kind of independently of the literature, because we did it first, but they kind of came along slightly later, and they evolved an approach to that was pretty much indistinguishable to continuous delivery. The bottom line, once they'd made that switch, was that 8 times as much effort now went into creating value for the organization, creating new features. If you look at the breakdown of the work that's going on the right-hand side, it's really, really quite different. It's really very significantly different to the picture on the left. There's a lot of effort going into writing tests, automated testing, continuous integration, and all those sorts of things. One of the pushbacks that I often get from clients is that, yeah, but we don't have time to write all those tests. But it's like dieting or exercise. It's not time spent. It's not a cost. It's an investment. If you spend time writing tests now, that pays back in spades later on. The bottom line is 8 times as much effort going into creating new software. Overall development costs were reduced by 40%, at the same time increasing the number of programs under development by 140%. So development costs per program went down by 70%. Remember what I said, we're not talking about a 5 or 10% improvement here. We're talking about massive changes in the effectiveness and the efficiency of software development. This is captured in this really good book called A Practical Approach to Large-Scale Agile Development by Gary Groover and a couple of other guys. Gary wrote most of it, I think, to be honest. What we see, the kinds of numbers that we see from peer-reviewed analysis of industry across the board, we see things like 90% lower defect rates on these sorts of teams. And my presentation has stopped. Come on, next. Excuse me. I probably shouldn't have pressed that button, it stopped. We see things like 90% reduction in defects. We see teams that practice this kind of approach to development will spend 44% more time on new work, and they will spend 24% less time on unplanned work. They'll spend 50% less time on fixing security defects and those sorts of things. The bottom line, though, is that organizations that do this kind of thing make more money than organizations that don't. This is from analysis across the industry. If your organization, the organizations that practice this kind of approach to development make more money than organizations that don't. I have a friend that does stock trading, and a couple of years ago he decided that he was going to, just as an experiment, he was going to invest only in organizations that talked about DevOps or continuous delivery as part of, publicly. And he only invested in those organizations. He's currently 112% above the Fortune 500 in terms of the performance of his investments. So what's my point? My point is that continuous delivery changes the economics of software development. It's radically different. And so my belief is that it's going to impact on you at some level. Either your organization is going to start working this way, and you're going to have, it's going to be interesting, it's going to be fun. People like working in these kinds of environments. They're liberating kind of environments. But there's going to be a lot of stuff. There's a lot of stuff to start to apprehend and to adapt to. Or your organization is not going to make that change, and at some point one of your competitors will, and when they do, they will beat you, because this is a more effective way of building software. Organizations that practice it, the usual suspects: Google, Amazon, Netflix, Spotify, those sorts of places, but places that you wouldn't think of as well. SAP are doing some really interesting work. I'm working with a bunch of healthcare companies at the moment. One of my clients is Siemens Healthcare. They're doing continuous delivery. Volvo Trucks, a modern Volvo truck is a complicated computing platform, 80 million lines of code. They've gone from taking 6 months to have a single line change of code and getting that into a real truck on a test track to 20 minutes. This is a dramatic change. At that point, without any slides, I think I've come to an end. I think I've probably got time for a couple of questions. Thank you very much.